You think we have made great progress on weather and climate forecasting, but considering global warming that's happening and how that's affecting the weather and climate forecasts, or weather and climate in locally, and how we need to provide information at as high a resolution as possible. Now this is often referred to as hyper-local forecasts. Obviously they mix not just models but also data and AI approaches and so on to bring forecasts down to local scales. For various applications, we have talked about S2S applications, we have talked about S2S for food, water, energy, health, transportation, and so on. And there is also need for climate information for adaptation and mitigation. So this report is this paper in BAM's Bulletin of American Meteorological Society came out last year. It's basically a summary of a World Meteorological Organization report. I am summarizing it because it has some nice points and is very timely and relevant for the need for information, especially in the so-called climate services sector, where we are trying to go beyond weather services and provide early warnings, which are one of the key tools for adaptation, especially for the global south and developing countries and poor countries. So it's titled Advancing Weather and Climate Forecasting for Our Changing World. Here are the team of authors who have been involved. There are some big names. You've probably seen many of these before. Tom Stoker was head of IPCC. Alan Thorpe is at Albany. Tim Palmer is a big name now at Oxford, was at ECMWF for a long time. Let's read the abstract and then make a few additional points. It has a nice table of history of evolution of weather and climate forecasts, which are very interesting things to read. Our world is rapidly changing. Societies are facing an increase in the frequency and intensity of high impact and extreme weather and climate events. As I said, this is why we need to revisit again and again this idea of advancing weather and climate forecasts. These extremes, together with exponential population growth and demographic shifts like urbanization, increase in coastal populations, are increasing the detrimental societal and economic impact of hazardous weather and climate events. Billions of dollars are lost, but also many lives are lost, and millions of people are displaced. So these are critical things. Urbanization and our changing global economy have also increased the need for accurate projections of climate change and improved predictions of disruptive and potentially beneficial weather events on kilometer scales. I have a podcast on case scale modeling, which also included Julius Slingo, Tim Palmer, and so on, beyond Stevens. Technological innovations are also leading to an evolving and growing role of private sector in weather and climate enterprise. This article discusses the challenges faced in accelerating advances in weather and climate forecasting and proposes a vision for key actions needed across the private, public, and academic sectors. Actions span utilizing the new observational and computing ecosystems, which are always important for running these models at higher and higher resolution. Strategies to advance Earth system models, because increasing resolution is a brute force approach, but we still don't know whether including the Earth system feedbacks like from vegetation, carbon, human activities improve the forecasts better than let's say increasing resolution. Ways to benefit from the growing role of artificial intelligence. AI, for example, will take any forecast from the native resolution of the forecast model to decision scales, local scales. Could be a farm, could be a neighborhood in a city for a heat wave or a event of other floods and droughts and so on and so forth. Practices to improve ways to benefit from the growing role of artificial intelligence. Practices to improve the communication of forecasts, information, and decision support in our age of internet and social media. And 5, addressing the need to reduce the relatively large detrimental impacts of weather and climate on all nations, especially on low-income nations. These actions will be based on a model improved cooperation between model of improved cooperation between the public, private, and academic sectors. Academia often does blue sky research, individual intellectual curiosity driven science, but can they begin to form teams to work together to solve bigger issues that don't get addressed at individual levels? Funding and evaluation metrics also have to change to give credit to academic researchers for doing these things. This article represents a concise summary of the white paper on the future of weather and climate forecasting published in 2021, which was put together by the World Meteorological Organization's open consultative platform. Okay, so just to start off, geographical overview of relevant weather-related loss events worldwide were 1980 to 85, and we'll compare it to a recent period to show how they have increased. So these include small, medium, and large loss events. There is a definition behind them, and there are catastrophic events, and they include meteorological events like tropical cyclones, extratropical storm, convective storm, locust storm, hydrological events like floods, mass movement. So 1383 registered events also include climatological events like extreme temperatures, droughts, and forest fire. So this is coming from Munich Re, which is a reinsurance company, but you can see that pretty much the whole world is covered by these weather and weather-related loss events. Where there are no dots, it doesn't mean nothing happened. It's just that there are no data logged in from those regions, but we can be pretty sure that there were extreme events happening over Eurasia and Japan as well, right? Geographical overview of the same thing for 2013 to 2018. You can see the map has become much more crowded for all colors, especially rich countries. So Europe and US and India has gotten so many more dots, especially in hydrological events, and so is China here, for example. And you can be sure that this is still not fully representative. There are more dots here now because you have more data being reported as well compared to the period here. So we are having more reporting and also more events, and population has increased over that period, and coastal populations have increased here. Droughts here have become more prevalent, and maybe that's the natural condition for the eastern part of the Pacific, which goes back all the way to the Mayas and Incas, and how they may have gone extinct due to persistent droughts and so on. So rich countries experiencing these kind of climate events raises the concern enough that they will not ignore it as a problem of the global south, or they will not assume that they are immune to climate change. So these have some sort of benefits in a kind of a perverse way. The innovation cycle imagined here, the public-private academic engagement challenge taken from Brunet et al. The operations component is the creation of forecast and other products, while service is the delivery of these products to stakeholders and customers. So that's the climate service that I mentioned, which is becoming more and more prominent now, especially at the sub-seasonal to seasonal timescales. Note that each sector can make contributions to the various components, such as research and development, operations, and service. I've left the door and the window open, so there's a bit of a breeze, but hopefully the sound quality is not getting destroyed. So here is infrastructure at the center in terms of observations, computations, including satellites. You need research and components with participation, co-production with stakeholders and customers, and they are coming in also into operational part of it. The last mile problems of translating forecasts to decisions are always kind of socio-economic decision making processes at local governments and regional and national, sometimes international, like for the pandemic. And of course that's the service part here. Looking at the major milestones in operational weather and climate forecasting, 1861, Met Office weather forecast services using telegraphs established by Fitzroy. You can read more about it in the paper with the reference. 1873, working toward global meteorological observatories and international data sharing with Foundation of International Meteorological Organization in Vienna. 1873. 1900 to 1922, birth of numerical weather prediction with the work of Abbey, Bjerknes, and Richardson. He did the first parallel computing sort of thing, collecting people in a room and having them pass computed information to each other to build towards prediction. Obviously, he took a long time to make a 6-hour forecast and so on. Early 1920s, onset of statistical climate prediction and global atmospheric teleconnection insights pioneered by Gilbert Walker, Sir Gilbert Walker, who came up with the Southern Oscillation connections to monsoon droughts. 1950, first computer NWP forecast on electronic numerical integrator and computer ENIAC by Charney et al. So John von Neumann was the guy who was already imagining using weather as a way to control wars and geopolitics, so you can imagine. 1960 onwards, satellite-based meteorological observations and telecommunications at the forefront of technological innovation since the launch of TIROS-1, the first weather satellite. 1960s onward, emergence of general circulation models for climate research and forecasting. So, Manabe, Kirkbride, and of course, Charney was already playing a role. 1962, establishment of the World Weather Watch program with its three main components: Global Observing System, Global Telecommunication System, and Global Data Processing System. Visionary ideas. 1963, Lorenz's seminal work on chaos initiated atmospheric predictability theory and paved the way to numerical ensemble prediction in the 1980s and 90s. So Lorenz basically pointed out that small errors in initialization can lead to large errors in weather forecasts after a few days, and then we realized with Charney and Shukla that there is a predictability of the second kind, where ocean forcing can still give forecasts as seasonal and longer time scales, even though weather becomes chaotic after a few days. Launch of the Global Atmospheric Research Program, GARP, led by Charney, happened in 1969. 69 onwards, global numerical weather prediction innovations since the first global spectral NWP simulation by Robert, oops, I chopped off the name there. But nonetheless, spectral models represent the grids in a way, and the finite element, finite volume models are different. They are gridded models, which are basically dividing the Earth into grids, X and Y grids, and so on and so forth. 1975, Federation of Global NWP R&D effort in Europe with the foundation of the European Center for Medium Range Weather Forecast, which is still a significant force in global weather forecasts and climate forecasts. 1979, first GARP global experiment to gather the most detailed observations ever of the global atmosphere. 1980, World Climate Research Program, WCRP, established under the joint sponsorship of WMO and the International Council for Science, currently the International Science Council. So WCRP is now a big coordinator of many activities, including the IPCC's assessment, simulations, and so on, scenarios, etc. 1980s onward, development of coupled ocean atmosphere climate models. 1992, operational implementation of ensemble prediction system at ECMWF and the National Centers for Environmental Prediction. They have competed with each other, and US had fallen behind on computational resources because of its own constraints. They had to use Cray and not buy Japanese machines and so on. 1993, Intergovernmental Oceanographic Commission of UNESCO became a co-sponsor of WCRP. 95 to 97, global reanalysis developed by NASA, NOAA, NSCAR, and ECMWF, fostering the use of NWP analysis in climate monitoring. I have discussed reanalyses elsewhere that you can look up. It's a blending of data and models to produce continuous records of the past in a kind of well-gridded format. There are many issues, but they are very useful products. 97, groundbreaking numerical prediction advances in the use of multiple sources of Earth system observations with the introduction at ECMWF of four-dimensional data assimilation. 98, World Weather Research Program established by the WMO. So you can imagine WCRP came well before WWRP. Reasons for that. Earth Simulator Japan, a landmark supercomputer investment for climate, weather, and geophysical research, produced some amazing results. 2002, Met Office began the use of high-resolution convective allowing model for operational prediction. If you know what that means, good. Otherwise, you can look up my other podcast. Basically, convection is represented in a statistical parameterization sense in models, but if you have high enough resolution, you can allow first principle kind of process representation of convection. Coming closer, 2004, WMO establishes the 10-year THORPEX program to accelerate improvements in the skill of global NWP model. That's the observational and research program. 2005, first operational assimilation of cloud and precipitation affected satellite data at ECMWF. 2007, a great step forward for weather and climate Earth system forecasting with 3,000 Argo oceanic floats in global operation. 2008 onward, dealing with prediction uncertainty in data assimilation with ensemble data assimilation techniques. If you don't know what that means, you can look up on my other podcast, but improving the blending of data into models to initialize forecasts is a very complicated and complex issue, and many improvements keep happening. Ensemble basically means you make multiple realizations so that model spans the reality and random errors can be reduced by averaging them. So ensemble means tend to have a better skill of forecasts than individual ensemble members, and so on. 2008 again, first successful launch and application of CubeSat technology by the University of Toronto for atmospheric profiling of column integrated CO2, atmospheric humidity and electron density. CubeSat, small satellites are expected to make a revolution in data gathering. 2013, first global simulations with sub-kilometer scale horizontal resolution conducted using non-hydrostatic icosahedral atmospheric model on the Case supercomputer. Terminology, if you don't know what that is, that's good. 2013, cloud computing first used for regional NWP applied to user needs. Basically, you are using distributed computing resources on the network rather than having it all in one place as a supercomputer. Agreement reached in the ECMWF system in 2014 between the annual average of the ensemble spread and error in increasing reliability of ensemble forecasts. So this is a nice big topic that we'll not touch on more details here. 2015, development of a 40-member ensemble member for the atmospheric component of the Community Earth System model. This is CSM from NCAR in the US, which is now going in advanced directions. 2018 onward, introduction of a coupled ocean sea ice model to global NWP systems, example leading to improved medium-range prediction of Arctic cyclones. So you have short and medium term, 1 to 3 days, 3 to 10 days. In the mid-latitudes, the systems move slower, evolve slower, so you can make longer-term forecasts compared to convective systems in the tropics, for example. 2018 onward, again, acceleration in the development of coevolution neural networks and other machine learning approaches for accelerating computing, advancing model physics, and weather and climate forecasts. Now AI and ML into climate forecasting has taken a much bigger role with a lot of new funding coming in to maybe develop data, models for clouds purely based on AI and so on. So you have to wait and see how they do. 2020 onward, joint weather and climate community initiatives toward global convection resolving models through the use of exascale computing. So computing resources have grown tremendously over time, and they have allowed many advances to happen and many higher resolution forecasts to be issued, which have to be skillful as well, and applications of those follow based on the resolution at which they are available. For example, a heat wave can affect different neighborhoods in a city itself very differently, so having forecasts at that scale could be very useful. Whether the numerical model will take us there, or we have to use AI and ML to downscale from the intrinsic resolution of the numerical weather models and so on, have been discussed a lot, and I have discussed it elsewhere, but here we'll just focus on the further details on the role that WMO has played over the years, and then look at some recommendations from this group. Okay.